Okay, good morning. Welcome. This is the latest webinar from EA Technology down in Australia. It's 10:30. We're going to kick off. So today we have myself, Neil Davis, and Thomas White talking to you about how to prevent failures before they happen and monitoring of partial discharge, really. Okay, so we are EA Technology. We've been here for a long time now, so nearly 60 years we've been operating and innovating and working with owners and operators of power networks. So the electricity companies and all the large users of electricity. We have 5 offices still headquartered in the UK. Global offices in the United States, Singapore, China, and here in Brisbane, which we've been for the last 12 years. So nice and happy, and working with the same sort of companies again across the world, all the large utilities and power users. So we know the networks pretty well, and that's really what we're going to talk about today. So the agenda, we're just going to go through very briefly on what is a partial discharge and what are the systems, but we're going to concentrate more today on the why and when and how people are using this to derive and to generate benefit. And like I say, at the end of it, we've got that session for questions. So feel free, pop those in to the Q&A box anytime you wish. Okay. We're in major trouble with that bit. Okay, let's just talk about partial discharge testing methodologies. And like I say, this is just a very quick overview. If you're here interested in monitoring, if you want to know the basics, then again, go onto the YouTube channel. There's lots of webinars and content on there which talk about this in much more detail. But realistically, for monitoring and the solution that we're going to be showing today, or we're going to be showing the results from that today, there are 3 major techniques that we use, or 3 major sensor technologies. So we have the transient earth voltage sensor, and we have the high frequency current CT, and we have ultrasonic sensors. Now, how and where you deploy just depends on the asset, where the asset type, and the asset location. So outdoor, if you're looking at outdoor assets, then we wouldn't put ultrasonic, obviously, because the range is coming into the sensor, and also rain on type of assets just generates huge amounts of ultrasonic, as does wind. Any rain or any turbulence generates lots of ultrasonic activity. So for outdoor assets, you would concentrate on HFCT around Earth, on cables maybe, or sometimes on plant, and you would concentrate on transient earth voltages on the outside of the Earth metalwork. That could be on the outside of a cable, it could be on the outside of a circuit breaker, bulk coil circuit breaker, or whatever it is, really. When we go into indoor, then indoor air insulated switchgear ultrasonic becomes a really significant sensor that you need to use, because you're looking at surface tracking on air insulated components. What we say, you can see in the slide here in the diagram, we have the HFCT and the TEV looking at discharging the cables, and the HFCT, TEV, and ultrasonic looking in the switchgear. This is effectively assuming that the termination is part of the switchgear. So if we're looking at terminations, then TEV and ultrasonic are 2 of the primary techniques. HFCT will also find that, but TEV and HFCT will allow you to look down the cable as well as looking locally to the switchgear. So they're the sort of sensor technologies that we use. Okay, next.
Sorry, me answering questions.
Okay, so where they use and what defects do they apply to? Ultrasonic is not going to find internal discharge, because you need a line of sight, you need an air path to that. So for internal discharge, it's transient earth voltage and HFCT. We can use the HFCT to look up to the switchgear and the termination area, as well as looking down the cable, just depending on the frequency and filtering that we put on that. Corona discharge, not something that we're typically looking for. Usually it's non-destructive, but it can become an issue in indoor switchgear. Corona discharge is primarily detected using the ultrasonic technique. If it's really high, you might get some TEV, but particularly ultrasonic. But again, mostly non-destructive, so not something we're particularly interested in. Surface discharge, on the other hand, is something that we're very interested in. Now, surface discharge, whether that's phase-to-phase discharge between cable phases, for example, tracking across resin-type insulation, epoxy-type insulation, that can be very serious. That can accelerate away quite quickly. The most sensitive way of detecting that is through the ultrasonic detection. If it's high, there's a large component to earth, then you're also going to detect that using the electromagnetic techniques of transient earth voltage or HFCT. So we will always use HFCT no matter what. Ultrasonic is when we're targeting towards air insulated components. You also have contact discharge. This is another type of discharge that sometimes in high voltage switch yards is not massively a problem. If you got maybe bus bars, rollers and slight gaps, and you got metal to metal discharge in a switch yard, not particularly a problem. The byproducts of the discharge are going to dissipate just like they do with corona, and not going to cause too much of a problem. But it causes local noise, which can mask other things out. If you start looking at contact discharge inside switchgear, then again, it can be a significant problem. So really, it's a different type of discharge that we need to detect with that. That will generate high transient earth voltages, high HFCTs, so the same thing, electromagnetic discharges, and also that can generate high ultrasonic. So the combination of the sensors and what the PRPD pattern looks like with the sensors allows us to diagnose the type of discharge, and effectively that's one of the parameters that goes into determining the severity and whether you want to go and investigate and when you want to go and investigate. Okay, so that's the sensors. Let's briefly look at the system that we are using, that is all the case studies that we've got coming up are detected through. It's the Astute HV monitor is what we have. It's a modular system, so it enables us to look for small switchboards, large switchboards, same piece of kit. We have a hub, which we can see in the top left image there in an indoor substation on the wall. There's an outdoor version in a cabinet that we can see in the bottom left. And then we have a series of nodes which are placed along the switchgear. The nodes themselves will have an inbuilt transient earth voltage sensor, and it will have plug-in sensors for ultrasonic, which you can see pointing in the top right there up towards a circuit breaker spouts. And in the bottom left, you've got, again, transient earth voltage sensors on the nodes themselves and ultrasonic going into the cable chambers on that piece of switchgear. So we have very much flexibility in how many sensors we want to put across the switchgear. The key thing for older retrofit onto older equipment, which is a lot of what we're going to be talking about today, is that you don't need a shutdown to install it. So it's completely non-intrusive. You're not having to take an outage. You're not having to go and install sensors anywhere in the system. Okay, so the TEV sensing through the nodes, and there's also external sensors that can plug into the nodes, so you can have 2 per. They're all basically magnetically done. Communication, we usually do this via a 4G modem, so it saves you going into your corporate network and all the cybersecurity risks and 1,000,001 questions from the IT department. Okay, so why? I'm going to talk a little bit now about the reasons that the general reasons that people will use it. So monitoring versus periodic testing, really. And one of the big things is that you're testing under all different conditions. So you're testing under different environmental conditions, under different network arrangements. Over the past many years where we've been testing, we've all come across the sort of issues where you're going in to test a switchboard. A particular circuit breaker is open for a day because maybe a pump is not operational at that time, and then when the circuit breaker closes, the pump comes in and there's a discharge on the on the the portion after the switchgear. So on the fixed portion of the switchgear, if you like, on rackable switchgear in the CTs or the cable termination, there's a discharge. If we just go by the first test using a handheld on the day when the circuit breaker was closed, then we can potentially miss that. If we're not going back for another year, then that could be a discharge that we missed. Environmental, another key point. If you look at the sort of environment that we have down here in Brisbane, this time of year it gets quite critical because we have these shoulder seasons where we have big swings in humidity. As the nights are getting cooler and the days are still relatively warm, we get the swings that generates the dew point changes, and we can have high humidity, and that can cause discharge on surface. So surface discharge is very much driven by obviously defects, but also the level of humidity in the atmosphere. You go and test today and it's quite dry, sun shines up, it's a dry, low humidity, then you may not find a problem. You go and test tomorrow when the humidity has come back up, you can see that a discharge is present. So again, operating under all those different conditions. If you have a very critical board and you're wanting to test this frequently, it becomes labor intensive. So if you put a monitor on, that takes it away. If you've got people working in substations for a prolonged period of time, let's say they're doing a protection upgrade or they're doing some other work in the substation, then or in the switchyard, of course, then you've got the situation where you're next to a piece of switchgear. If there's a potential for a problem in there, having a monitor on, letting that alert you is going to increase the level of safety and de-risk the prolonged period of time that you're working in the substation. But the absolute key thing is all around its the ability to capture shorter P2F interval failures. We'll talk about the P2F interval now. So if you're familiar with the RCM type approach to this, the reliability centered maintenance, there's the concept of the P2F interval of when you can start seeing a defect or a failure occurring. So the defect is visible in condition monitoring to the point at which it functionally fails. That time has to be long enough for you to act for condition monitoring to work. Now, if you've got a very known defined period, so it's the defect is exactly the same in exactly the same location, and let's say it's for 1 year, then going and doing a 6-monthly survey is absolutely applicable to finding every single fault if it only fails in that time and it's always a P2F interval of 12 months. When it comes to switchgear and cables, then all the different failures will have unique P2F characteristics. It depends on the type of discharge. Internal void discharge, solid insulation will generally take a long time. Surface discharge can track and go to failure very, very quickly. So the type of asset, the amplitude, the insulation type, the environmental conditions. You put a surface discharge in a damp substation, failure will happen much quicker than if you put a surface discharge in a very dry humidity controlled substation. So all of these things play a part. So identifying the amount of time is very variable, but you need enough time from the point at which you detect to the time of failure in order to plan action and do something about it. Okay, let's click on that one. So it's different. Now, the whole point about monitoring is you will get that warning very early, and that will give you the optimum, it'll give you the maximum amount of time to test. So you will get some, if for an example, instead of the 1 year P2F interval, we have a 4-month P2F interval. So from when it instigates, when you can see it to when it fails is only 4 months. An annual survey is only going to give you a 33% chance of finding that. So the earlier defect can be detected, the better, and that allows you to effectively reduce the probability of failure on the basis that if you find it and you can act on it. So the more you monitor, the the more chance you've got of acting before failure occurs. So that's the reason of why we use the monitoring in our to condition monitor switchgear. Okay.
And that really takes us to when should we be implementing it? So what are the user cases? What is the business case for us to really get these systems and implement it into your networks as asset engineers? Because it's knowing when to correctly apply this type of testing, because it's not always the fit in every scenario. It's always about making sure that it is the right user case for it. And what we've seen is a number of different ones, but we're going to go through them one by one and talk through. So monitoring a known defect is a time when condition permanent monitoring becomes quite useful. So a lot of you on your HV networks will be doing point-in-time testing or other condition monitoring tests, and you hopefully will be identifying some defects through that scenario. So the question is, what do you do in the time between you've identified that problem to you're looking to do the maintenance or to do a repair? And monitoring can be a really good solution to that. It allows you to trend a problem as it leads up to a shutdown period, allowing you to know if you need to bring that forward or if you can push that back. And it allows that just additional level of one, safety for workers in the room leading up to that point, but surety that you're not going to have that the outage that you're trying to avoid before the scheduled one. One thing that is really critical is when you are doing maintenance, and if you are monitoring up until you can perform maintenance, is we always recommend leaving the system on after you do manage to perform that maintenance. And a perfect example of this is what you can see here on the right. So the first picture is what the boots looked like before they performed maintenance. So they went in, they actually found it was a loose connection. They did that repair work, and then they put the system back in, they continued to monitor it, and over the next 2 days, we found incredibly high level PD coming out of that board. The picture on the right is what the boots looked like after 2 days of operational use. And what it was they forgot to put in the earth drain wire on the HV boots. Relatively simple mistake, but quite critical, and the amount of damage, and if that was left, and as Neil said, tested again in a year, a lot of damage would have happened if that occurred after simply 2 days of activity. So it's one of the things we always recommend to people, that you do give yourself a little bit of leeway, make sure that the repairs have gone well, there's been no new defects introduced, and it allows you to keep track of the asset. But let's have a look about what is the business case for that. So if we look at that particular scenario, it was on a renewable generator, it was on their primary 33 kV switchboard, and it was 13 panels. For this particular site, that outage cost them in generation about $50,000 per day for that feeder, which is quite conservative once you come to outage costs. But the big thing is that board was only 5 years old. So once we start to actually look at the risk calculations and everything like that, and we look and we go, well, what risk does that board and those defects carry to their network? If it had have kept going and kept grading, you're looking at around $300,000 to $400,000 of risk reduction simply by installing the monitoring system. So if we look at it on a per year basis, by installing the monitoring system and by basically alerting the engineers, allowing that planned maintenance, you can offset the risk and you can bring that down, reduce the probability of failure, and overall you have a lower risk board. This particular system, over 10 years, you're looking at saving between that $300,000 and $400,000 mark just in the risk reduction through monitoring. And that's for a very young board. The one thing that we should all hope is that when you've got a board of 5 years old, you're not having multiple defects installed into them that early. But the question does arise that the terminations that they went, and they didn't actually inspect every set on the way through, is, are there other defects that were installed at the same time? So do you have the trust and the faith, and is installing monitoring giving you the peace of mind that you know if any other issues do start to creep up, that you will detect them without an unplanned outage causing it. So then we move on to things like the older boards. De-risking aging assets is one of the really critical reasons that people will install monitoring, and it's the best user case that you will come across. And you can approach de-risking aging assets from a number of different perspectives. So once you've got an old board and it is getting towards that end of life, once you start to monitor it, there's a couple of things that you can do. One of them is if you have a known replacement of that board, you know in 5 years that you are going to replace it, you're just looking to nurse it through retirement. You may have a couple of known PD sources that you don't want to do major works to eliminate, but if they are steady, if they're not trending up, like the internal voids that Neil was talking about, at that point, having a monitor on them to prove that they aren't increasing or decreasing, keeping an eye, can help you defer some of that expenditure for the maintenance until you can get to that replacement that you've planned. What's even better is the flip side. Say you have got an older board, it is getting there, but it is in generally good condition. You can do the opposite and you can look at extending its end of life. You were thinking that maybe at 55 years old, you may have to look at starting to replace the entire board, but you haven't experienced problems with it. All of your condition monitoring tests are telling you that the board is in good health. So what you can do is use condition monitoring as a tool to say, let's extend the life of this board, let's keep a closer eye on it, and then let's defer that capital expenditure and use it elsewhere in your network where you do need it. So let's have a look at how that plays in terms of the risk calculations. So this is an example from the first scenario I was talking about. A 25-year-old board, a 25-panel board of 11 kV, which would be a primary zone substation in Australia, and about 45 years old. So it is getting towards its end of life scenario. This particular one that I've modelled is in a DNO in Australia, and they're looking at around $200,000 per day costs for de-energisation. This one is it has known PD issues, and overall they'd think it's in quite a poor condition. So once we start to look, in year one, you're looking at around the $100,000 to $200,000 worth of risk that board carries. In year one alone, by installing the monitor, you can decrease that down to around the 50,000 mark, and you're nearly reducing the risk of that board by the 100,000. But of course, the health of that board doesn't stand still. Over the next 10 years of your life, that board is going to continue to degrade, it will continue to age, and its risk will naturally go up. But once we do start to look at the plots, you can see how over the lifetime or the next 10 years of that switchgear, how much you are drastically reducing the risk by installing the monitor, keeping it on, doing the targeted maintenance. So overall, they'd have a total reduction of risk of nearly $2.5 million just by installing monitoring on a board of that scenario. So let's look at the flip side of that example. Let's look at a very similar board. So a 30-panel board at a zone substation, 65 years old now. So you're looking really towards its end of life. But let's say it's a little bit more critical. Let's say you're looking, rather than $200,000 per day de-energisation, you're looking at $500,000 per day. So this particular board has got quite good condition monitoring results. It's got no issues and it's got good overall conditions from other tests. When we start to look at the risk of this board, whilst it is quite high naturally, if we look at it in all of its different stages, so this one is approaching its end of life, and its risk right here is approaching up to the $200,000 mark. If we were to install a monitoring system on it, we can see that the risk is significantly reduced and almost or even further than if it was considered to be book life reached or even more than average condition. So what you can do is it's use things like this and the risk profile of your board as justification to if you do want to start to extend the life of your switchgear. And it can be a really good tool, especially if you just need a couple more years to get it through a project or to get it, the capital you need for a larger replacement program. We then move on to the scenario where you have population defects. And I'm going to do a quite big example of this towards the end of the webinar, but there is a chance that you will have population defects in a specific asset type or manufacturer or something or region where you have a known problem that is causing you grief. This elevates the risk of not just one asset type, but your entire fleet of those particular assets. So monitoring can become really critical in that scenario once you start to pair it with a larger kind of handheld or point-in-time testing fleet. So in the scenario, say you have an RMU where you've got hundreds or potentially even thousands, you can do a large point-in-time testing where you go out, you test everything, and you build your profile of health across the asset range. From there, you can identify your top 5, 10, 20%, depending on the numbers. Then you can look at monitoring those particular assets. You can look at trending those and then figuring out if those sources are degrading quickly, if they are degrading slowly, if they are holding steady. And that way you can build nearly a model of the P to F curve based on your population. If you do start to monitor and you see that those particular assets have quite a low P to F curve, that's when you, P to F interval, that is when you start to make planning. You say, look, if we do find these problems, we have 3, 6, 8, 12 months until we need to do repair or replacement. The opposite can also happen. You can see that the defects aren't growing, that they are holding quite stable, and then you have a little bit longer to deal with the problem. But we'll talk about this later on. Critical events causing increased risk is one that we are seeing more and more, and we've done plenty of work in Australia and worldwide where the spotlight has been on, be it World Cups, I believe. We've done some work for the Olympics, and no one wants to be caught losing power to a World Cup event. So there are times of heightened risk where you do want to put that little bit more effort. You may want to put a little bit of short-term monitoring or monitoring in a period leading up to that event, so you know and you understand the health of the assets that are critical to that event. A really good example of this comes out of Indonesia, where we did work. We teamed up with some of the local electrical authority there, and we installed monitoring on a critical switchboard that was providing power to the G20 summit. What they did is they did put this in, and they actually found quite a high level ultrasonic type issue. And as Neil discussed earlier on, your ultrasonic issues traditionally can have a very small P to F interval. They can snowball quite quickly, and they can go from inception to failure quite quickly. So by putting this system on, they were able to identify that. They were able to localize it down to the exact chamber it was in, find the problem, get the scheduled outage where there was nothing interrupted, go in and repair the work. Luckily, in this scenario, it was quite a simple fix. They had in one of the main incoming cable chambers, 2 sheds were touching, so they removed the sheds, cleaned up the terms, and there was no major damage. But it's a really good proof point that if this had have been that very low P to F interval and this had have lost power mid-summit, it's never what you want from a political point of view. Although I do think losing power during a World Cup would potentially be more damning.
Yeah, you don't want to be showing the bad side to the world when a few 100 million people are watching.
Improved safety is one that we are working with more and more with companies nowadays. As assets are aging, especially some of the trickier to deal with assets, such as your pitch field and oil field assets, risk to workers is really becoming one of the biggest issues that we talk to people about with monitoring, and how we can use the monitoring to de-risk and make everyone feel a bit safer in the room. So we've got a number of programs that we work with companies. Some companies that have full restrictions to access to the substations use the monitoring data prior to entry as part of their JSAs and their no-go or go or no-go entry to the sub. So what they can do is they can pull up all the data from outside the switch room, they can look at it, they can assess if there are any high level, if there is anything trending up, if there is any PD activity emerging, and they can make the judgment call if it's safe to enter before they do. And those systems are used in quite a permanent scenario on those rooms. Other companies are actually using the systems as part of extended monitoring during projects. So what we do is when they do have an extended project, I think anything over 2 weeks of a worker in a room with the switchboard, they install the system 2 weeks prior in order to get a good benchmark of activity within that room. And then they actually have us monitor the board on their behalf. And what we do is we have a list of key personnel who will be on site on a daily basis. And if any alarms trip, if any signals start to creep up or anything untoward is there, the first point of contact for us is the workers who will be standing in that room. And that was a really good initiative put forward, because their biggest concern with the monitoring and the alarms going to the control room or anything like that, if you do have that very small PDF interval scenario, albeit rare, the people that need to know are the ones standing in the room with the switchgear and with the potential defects. So this is something that is cropping up more and more, especially on the aging assets. And those were very much the kind of key scenarios. Every business will have a different scenario and a different reason that they use monitoring, but those are just the ones that have popped up the most for us over the last couple of years. So where we kind of go with this is, if you do have one of these monitoring systems, how can you effectively use the data to manage your network? It's very obvious what you're doing when you're using it for those short-term PDF interval problems. It's a problem emerges and you're looking to fix it right away. But how can we use this data for more long-term planning? And really, it is all about knowledge of the switchgear. It is about knowing the condition of your asset and putting that forward into long-term planning. High-level defects may require immediate action, but as we were saying, the low and medium level defects that you don't need that immediate shutdown for, it's can you push them into scheduled maintenance in 6 months, in a year, or whatever you have coming on. A lot of networks that have redundancy do have the ability to do that switching quite quickly, and they may be able to de-energize that board and do maintenance on even low or medium level. However, once you go to industrial sites, places that don't have as much of the redundancy, you may only have a shutdown once a year or different things like that. So if you can monitor a low-level defect, ensure that it's not getting worse, and then push it through to that scheduled maintenance that is planned, you'll have a lot less loss of production, which makes everyone overall happier. And this is the general workflow that we tend to work through with the companies that we do the monitoring with. And it all starts with the installation of the continuous monitoring. The data is there. A lot of these companies will handle all that analysis and the alarming in-house, but we will also handle a lot of it for them. So it comes through. If any alarms are sent through, it's immediate. Otherwise, it's reports and analysis. And all of that will go through to the asset engineers. If there is something critical, the whole goal is to do the repairs quickly and immediately in order to ensure safety and everything. For the long-term ones, they can push it into their asset management programs, things like your condition-based risk management, the CBRM, or other programs that you may use to do long-term asset planning and forecasting. And those are the ones which are the low level or the intermittent that we start to play with. But The overall goal is long-term risk reduction and improved safety and reliability on site. So let's have a look through an example that really drives home a lot of the points that we have been talking about. So this is an example from a UK DNO, and what they've done is all of the right things. They identified a particular type of switchgear, Neil's favourite switchgear to be precise, that had a known defect. The type of cast resin used in the breaker bushings was particularly susceptible to surface tracking type discharge, and especially when it was in high humidity environments. So that was identified. They did a lot of work to know that, but they also had a population of those assets to manage. So they went through and they identified assets that were at high risk. And that's where this particular case scenario comes from. It comes from one of their substations that was right on a river's edge, quite a critical board, and due to its location had a naturally quite high humidity. They got into contact with us. We installed a monitoring system so it would be alarmed and they could catch any of those problems. When we initially went to site, there were no defects. They did a scan, they installed the board. However, 4 months later, they did have a failure on one of those circuit breakers. It was detected by the system, it was there, an alarm did trigger, but they failed on the one critical component where there was no communications set up between the monitoring system and the engineers. So there was no notification sent out, and no action was had. And that is the critical thing, because unfortunately, if you do put all these systems in, if you do get that early warning, you still do need to act. And that's the only really shortfall of the engineers in this scenario. They did all the right planning, they did all the right things, but it was
there was no communication, so they weren't getting the data.
Yeah.
So putting the monitor on is the start of the project, not the end of the project.
Yeah. And we can see that once we actually start to look at the data. So you can see when we were on site installing the monitor, everything was low level. There was nothing to detect, so you put it on. A little time later, you can see it starts to ramp up on the ultrasonic amplitudes and increase. So if we relate that back to the PDF curve that Neil talked about, that is the point at which the failure becomes detectable. That is where, if you were perfect, if you were standing there, you would be able to find it at that point. Our alarm triggered a little bit later, once it reached a little bit higher level and got above the noise bar, but that's within, I believe, a day or two. From there, you had just between 3 and 4 months was the PDF interval between when we detected it and when the failure physically occurred. And that is a very short time period, and especially if you're doing point-in-time testing rather than continuous monitoring. And it's a really critical thing to think about. This one, when it all went through and everything, with the fines that they received for the customer lost minutes, you were looking around 600,000 Australian dollars. And that's not to talk about the repair costs, the labour, the new assets, the cleaning of the panels around it. So I would expect that to be quite a bit higher once it was all said and done. But the thing to think about here is, would you have found that if you were doing regular 12-month interval testing? For 3 to 4 months, it is a low chance. If you're doing it 6 monthly, it does increase. But the one thing to think about is, if on your network and you had this type of defect, would you have been able to identify it and react in time to stop that failure? Because it is a very difficult one to get ahead of if you don't have the continuous monitoring in place. So overall, to go through what we've talked about today, monitoring of assets can be very effective in reducing the risk, and it can be employed to really effectively work for networks in order to extend their life, defer capital expenditure, and increase safety for the workers within substations. You can install it on both a short or a long-term basis to work with what your network requirements are and what your needs are. But if you are putting them on short term, especially leading up to maintenance, give yourself a little bit of leeway afterwards just to make sure it has been effective. The one thing with monitoring is it isn't a fit for every asset on your network. It has to be a business case, and it does have to work for the network. And you're always going to be targeting assets of high criticality. But the overall thing is, with any condition monitoring, to make informed decisions and to make good quality decisions, you need high quality condition data. And that's what the monitoring is all about. It's about getting you the best quality data in real time so you can make high quality decisions as you really take care of your network as it ages over time, which is quite good. So a lot of the graphs and the different views that you've seen throughout this are actually from one of our online tools, which you can go in and you can fill in a number of very simple questions. And what it does is a very simplistic breakdown of the CNAIM or condition-based risk management process. And it will determine the risk based on a couple of simple criteria. In this particular one, it's designed for switchboards, and it's the age of the board, the number of panels, your outage costs, and then does it have PD and what's its overall condition. So the way that we're quantifying risk in this scenario is looking at the different failure modes. So monitoring itself doesn't stop defects from starting, but what it does do is allow you to lower the probability of that defect evolving into a catastrophic failure. So for each asset type, when we start to determine how we're de-risking via monitoring, we basically get the breakdown of what is the likelihood of a defect going into a fixable incipient failure, a moderate failure, or a catastrophic failure, and installing monitoring lowers the number of catastrophic failures, the number of moderate failures, but then ironically in turn you have more incipient failures, which you can get to and fix during scheduled maintenance. So that's how the different risk categories are created for unmonitored and monitored assets. It's all about shifting the repercussions of a failure type away from that catastrophic failure with its large outages, with its large maintenance costs. And we did do a different webinar on that a little bit ago if you would like to learn more, because it is on the YouTube channel. But thank you very much for joining us. Hopefully you did get something from it. Both Neil and my contacts are there. If you do need anything, please feel free to reach out. You will get an email follow-up with the links and everything which we've shown in here in case you did miss them. But other than that, thank you very much.
And have a go at the risk calculator. It's there, free to use. Have a look at that and see what you can get from that. Thank you very much.
Thank you, everyone.